we looked at the linear function. We looked at the quadratic function. Next logical step, the cubic function. So let's talk about the cubic. Now the cubic actually has two different basic shapes. So it depends on which one we're looking at. The one we most commonly recognise with the cubic, y equals x cubed. So anything that can be factorised into a perfect cube, so something all cubed, might be some constant times that, but would have that type of shape. It's what we call an inflecting curve. At the origin there, that is in fact a horizontal point of inflection. Called that because if you were to draw a tangent, the tangent would be horizontal. Other cubics though will look like this. So it's a continuous curve, it'll have two turning points. So they're the two possible shapes of cubics. And just like with linear functions and quadratic functions, we can create every possible cubic out of these shapes using rotation, translation, reflection, and so on. How do we recognise it? No big surprise. There's our basic one. One of the pronumerals to the power of 1. The highest power of the other variable is 3. So let's move on to polynomials in general then. So all sorts of different shapes polynomials can have. I mean, they're all continuous and usually they'll all have turning points. But ones that can be factorised down to be a perfect factor, so whatever the power is. So a quartic to the power of 4, a pentic to the power of 5, and so on. We'll take on a common basic shape. Even powers will all have that U shape. Only the power of 2 is a parabola. Right? The other ones aren't parabolas, but they still have that U shape. Odd ones all have that inflecting shape. Now, what happens is, as the power gets bigger, the curve gets flatter at the base, steeper at the sides. So possibly I've exaggerated mine with that odd one. I've made it really flat at the base there and steep at the sides. But yeah, as the power gets bigger and bigger and bigger, you'll see that happening more. How do you recognise a polynomial? Our definition of a polynomial. Okay, well, we're still going to have 1 to the power of 1, but all the powers of the other pronumeral must be positive integers. Okay, so if you've got a fractional power, it's not a polynomial. You've got a negative power, it's not a polynomial. The highest power tells us what we call the degree of the polynomial. So a quadratic is a polynomial of degree 2. A cubic is a quadratic of degree 3, and so on. So let's talk about sketching polynomials, things to look for. So when you're drawing your polynomial, I've just called it y equals capital PX. The y-intercept is the constant, same as the linear function, same as the quadratic, whatever the constant is for the polynomial. We'll draw this one. Now I don't have to expand the whole thing out to work out the constant. I just look at all the constants in each factor and multiply them together. So at this stage we've got 1 times negative 1 cubed, so we're at negative 1, times 2 squared, so we're at negative 4. Let's plot that in. There it is, negative 4. Okay, x-intercepts are the roots. Solve the polynomial if it's easy to do so. My one's already factorised, so it's very easy to do so. There we go, there's negative 1, positive 1, and negative 2. Okay, now, as you approach infinity, all polynomials will behave like the leading term, the term with the highest power. Because when you start substituting in really big numbers, that highest power dominates the whole function. Because that extra power makes it so much bigger than all the other terms, it's like those other terms may as well not be there. All we need to do to work out where our polynomial starts and finishes is have a look at the leading term and work out where that would start and finish. So our one, again, I don't have to expand the whole thing out. I've got x times x cubed, so we're at x to the power of 4, times x squared, x to the power of 6. If I asked you to draw x to the power of 6, you would draw a U shape. It would start up there and it would finish up there. So now we know the direction our polynomial is coming from. The roots behave like the factor. So what happens on that x-axis is exactly the same as what the factor does if you were just drawing that curve alone. So anything with an even power will just touch like a parabola or a U shape depending on the size of the power. So on our one, over at negative 2, I know it's going to just touch, but I also know it starts up there, So our curve must come down and turn there at -2. Odd powers will behave that classic inflecting shape because it'll behave like the power. So over at 1, we've got a cubic. We know it finishes up there, so it must come through like that and inflect at the x-axis. Okay, in fact, there's our curve. Now at this stage, we're not going to worry too much about the vertex down the bottom where it is. Once we've done a bit of calculus and what have you, we can identify that exactly. So it's just a rough sketch at this stage. What would the shape of the curve look like? Circles. The most basic circle of all, x squared plus y squared, is the radius squared. Now when you are drawing these, now graphs normally, the scale on the y-axis does not have to be the same as the scale on the x-axis. You need a consistent scale on each axis, but there's no reason why it has to be the same on both. Circles are probably the exception to the rule, because if you don't make the scale the same on both, you won't end up drawing a circle, you'll end up drawing an ellipse, yeah, because it'll be all elongated or what have you. So for circles, it's a good idea to have the scale the same. Remember, circles are not functions. Fails the vertical line test. It is in fact made up of 2 functions. The top half of the circle and the bottom half of the circle. How do you recognize you have a circle? Both variables, the independent and the dependent, are to the power of 2. But more than just that, the coefficients are the same. Now in this case, the coefficient's 1. So you have 2x squared plus 2y squared, it's going to be a circle. If they are different, you won't get a circle. You'll get, what shape are we saying? Ellipse if they're both the same sign. If they're different in sign, we get a hyperbola. Functions that involve square roots then. When the dependent variable is made the subject of the function, often happens. So you might end up with the top half of the semicircle, or you could have a parabola on its side. They're now functions. So how do you recognize the shape? If you're unsure, square both sides, and it'll create something you recognize, hopefully. So there's the equation of the semicircle, y equals the square root of r squared minus x squared. I look at it and go, gee, I don't know. What is it? Square both sides and you very quickly see, oh yeah, circle. So I must have the semicircle because it's the positive square root of that. Same with our parabola over here. I don't recognise that. Square both sides. Y squared equals x. It's a quadratic. Got to be a parabola. In this case, parabola on its side. It's the top half because positive square root will be the top half of these shapes. Negative square root will be the bottom half of these shapes. Okay, that'll do us.